So you have a homomorphism, and a homomorphism is some kind of a map, say from some set A to B, and for some binary operation in A, say if A1 and A2 are elements of A, and there is some sort of binary operation between these guys, say A star, A1 star, A2, then, and let's call this the binary operation on A. Then the homomorphism, what it does is that, it's when acting on the result of this binary operation, it's going to be equal to the action on the individual elements and the corresponding binary operation in B. And so that's what a homomorphism is. And the group homomorphism in particular is when, A and B are groups, and the binary operation is like, group multiplication. Okay, so because of that, let me just go back and start the discussion of isomorphism theorem again today. Okay, are there any questions about this? Thanks to Nahi and Otono for pointing this out.
I have a question about this.
Yeah.
Tutorial question, the first tutorial question. Given the definition of a group homomorphism, doesn't the image have to be a group if F is a group homomorphism?
No, it doesn't have to be, because it doesn't have to be closed.
Oh, okay.
Because yeah, it's a very good question. Because B is a group, right? You're saying B is a group, so shouldn't the image be automatically a group? That's your question, right?
Yes.
So yeah, but you see, if you have a homomorphism, so from A to B, you start with A, and so this is A, but the group homomorphism can be such that, so this is B. It can be, so it can be such that, you only get a subset of B, right? So this is A, this is B, and this is your F. Now, what we know is that the whole of B is a group. So there is no guarantee that, the image of F, which may or may not be the whole of B, is a group under the same multiplication. It can be, that closure is, for example, satisfied, right? Or there's an inverse. Those things are not obvious. It could be that, it could have been that, there is some element G here, but its inverse is outside. And then there's G1 and G2, but, but when you multiply G1, G2, their product is outside. That could have been the case, right?
I don't think that's possible, given that F is a group homomorphism.
Ah, I see. Right. Okay. Oh yeah, I think that's a good, because we are saying that it's a homomorphism, not a group homomorphism. It's a group homomorphism, which means that, the fact that it's closed and all of that is no, I kind of don't agree completely, because it's a group homomorphism, but only with respect to the whole set B, right? And what we need to show is that the image of F is itself a group, and the fact that it's a group under the same multiplication, by assumption, it was not a group homomorphism for the image, because a map is not just defined by, it's not just defined, it's also defined by, the domain and the range, right? I mean, the fact that it is a group is basically a result that you prove, but it is not something that is obvious. It doesn't follow trivially from the fact that B is a group and F is a group homomorphism. Can you give your argument, Otonu or Saif?
I was thinking that since A is a group and that F preserves the group structure, so whatever it lands on in B must also be a group. I don't know if that's correct. That's how I was thinking about it.
Yeah, that's true. That's the definition of a group homomorphism, right?
So I think like just by a homomorphism, probably we can come up with counter examples. Like just as you said, it is not trivial.
Exactly. Yeah. So I mean, I agree with Saif, but what I don't agree with is that it follows trivially that the image of F is a group. Of course, by definition, B is a group. It is one of the assumptions of a group. But the fact that F acts as, it maps to the image of F, but, I can see, I mean, it is, if you think about it for a minute, you'd see that there's no other way, right? Because, what is the meaning of this rest of this stuff anyway, right? If it's a group homomorphism, why would this even be involved, right? Because, if F is not, if the purple area is the image of F, then the yellow area is something that, people from planet A, it's like the dark side of the moon. B is like the dark side of the moon, right? This map never sees, takes us to the yellow area, right? So I think I agree with Saif and Otonu, but at the same time, it's a trivial fact, almost trivial fact, but it's not. It should still be shown as should still be, demonstrated.
Yeah, I meant that it can be proved rigorously. That's why I said image of F is obviously a group.
Yeah, it is obviously a group because, it is obvious. I do agree, So essentially, the argument that I gave is part of the quote unquote formal, it's part of the formal sort of proof, but just because something is formal doesn't mean that it's not obvious. So I agree with you. I agree with both of you that it is obvious now that I'm thinking about it, because what else could it be? Because the map F doesn't, map onto any points in the yellow part, right? So, of course, the image of F must be a group. But to actually show that is something, one has to do. But I'm glad that, we have this discussion because, Does anyone else have any comments, or are people like really following what we are discussing? If not, I can try to explain what Otonu and Saif were saying.
No, I don't have any problems.
All right, so cool. Okay, any other questions or comments?